I'll do like some kind of intro.
Yeah, do an intro.
So welcome to working title Purely Functional Pleasantries.
Yeah.
I'm joined by Jonathan Lorimer, and my name is Ben Hart. We're Haskell enthusiasts, and we're going to talk today about functors.
Yeah.
Say hi, Jonathan.
Hello, everyone. I guess I'll kind of introduce the aim of this show. The idea was we're always having these discussions. We wanted to extend them to more people, and we wanted to record them for posterity, and we wanted them to be fairly casual, kind of like the discussions we were just having on our own.
Mm-hmm.
And so we wanted to take a topic that we had been learning, and unlike the classic trope of the monad tutorial where someone learns something, gets super excited about it, and then writes a blog post before they've established expertise, we wanted to focus on discussing certain quirks that we found interesting while learning. In functional programming, there are all these aha moments, and we wanted to focus in on those. So rather than talking from a place of pedagogy, we wanted to have more of an informal discussion. So I guess that will be the theme that guides these talks.
Yeah. And also we're not this isn't necessarily a discussion where we're gonna tell you everything about what Functor does.
Mm-hmm.
It's not like a tutorial per se.
Yeah.
It's okay, you've read Learn You a Haskell, whatever chapter it is where they get into Functor, and from there we could kind of have a launching off point of what's the other stuff that you've missed as you're learning Functor? What are the things that Functor's really good for beyond just using map? Things you might know it from other languages, if you're working in JavaScript or working in C# and using LINQ. What are you going to learn beyond the kind of initial intuitions about Functor that you may already have? Right.
I don't think we've made any decisions yet about category theory. I know that's something that we're both interested in, but I think as for now, we're going to keep it to just Haskell, which, there's plenty to talk about just within the Haskell ecosystem, as is. So maybe we'll pull stuff in, maybe we won't. I think, if we get a viewership, then I think we'll kind of cater to whatever they want to talk about. But other than that, I think because we're recording, we'll just kind of move ahead on topics.
Yeah. Let's kind of start off, and we'll just start talking with kind of the things we were discussing before the show started.
Right. So I'm going to share my screen.
So I think there's a general intuition about a functor has a map method.
Mm-hmm.
And if you have some container-ish thing, and it's not limited to containers, but I think that the general intuition is if you have some container-ish thing that holds something of type A, and you can provide a function that will transform it into something of type B, and then you can continue to do that. A really cool point that we're reading Dr. Boolean's Barely Adequate Guide to, or Professor Frisbee's.
Yeah.
It's written by Dr. Boolean, but it's Professor Frisbee's Barely Adequate Guide to Functional Programming at Work. Is the idea of mapping is actually an abstraction over composition, because you map, and you're actually composing things in a container.
Is that specific to JavaScript, or is that a feature of functors?
I think that's a feature of functors in general. Is repeated calls to map is composition within a containerized setting.
Interesting. Maybe this is actually a good segue into the functor laws, because I think you gave the basic definition of what a functor is, and maybe I can write that out. Is the idea of this class functor? I'm probably gonna butcher it, but it's in Haskell. If you don't know, we have type classes, and that's how we get ad hoc polymorphism, which is basically allows you to be to create these functions that are generic but have different implementations based on the types that they're given. That's how we would formalize a functor in Haskell, and
here we're formalizing like the concept of functor, and then when we have a functor, a concrete functor, we'll make it part of this class. We'll make an instance of the class for that.
Right.
Data
So
type. Yeah.
correct me if my syntax is wrong. I think it's you do the kind here. I might need a type.
Yeah. So here we're saying that some functor f will have kind star to star or type to type. So it's got to be something that takes some type. So like a list is going to take some type, and then it's a list of numbers, or a list of int, a list of string, which is just more lists underneath the hood. But it's going to have a functor, it's got to be of something, right?
Right. So maybe we can take a step back. I think we'll get into the kinds, because that was a bit of a moment for me. Was kind of thinking of a functor as taking something from kind to kind, and being able to reduce my types that way. And so that's a super important piece that I think we'll get to. But right now, I just wanted to write it out because you mentioned fmap. And so we could actually see that the type of this thing is it takes a function from A to B and a functor of A and gives you back a functor of B. So that's kind of the minimal definition, but on top of that, you've also got these laws. And these laws were something that were very difficult for me at first. I still don't think about them that much, but I'll probably receive a lot of flack for that, because I know that a lot of people love their laws. But we can write them out. And I think the first law, is the identity law, and that states that if you fmap identity, that's equal to just running the identity function on whatever functor you have.
Yeah.
And I mean, I know these laws are important, but this seems self-evident to me. It's like if you run an identity function on something inside of a functor, it's the same as just running an identity function over the whole functor.
Right. This law kind of keeps you honest, right? So it's got to say you're not secretly under the hood mutating something or even just having a counter of every function I run, I'm going to keep a count against how many functions were actually run against the thing that the functor covers.
Right.
Because that would cause a mutation that would break this functor law.
So my question to you, do you have an example of a functor implementation that would break this law?
Literally, if it has an int on it as a first parameter, and then you're operating over a second parameter.
Right.
Your implementation of map goes and increments the int, right?
Right. So let's do that. So say we've got we're gonna just make a type data identity A equals A. Oh no, we can't do that. So that's the thing. I thought that polymorphism kind of makes it difficult.
Okay, so throw your identity constructor in there. We'll call it unidentity because it purposely breaks identity. So throw int as your first parameter.
Hard code and int. Right,
yeah.
Right, I see.
And then you have a, sure.
Oh, great.
And then when you implement map with an instance.
Functor. Identity. Where? Oh no. Where?
I feel like this should be called undentity because it's the whole idea is that it breaks identity.
Yeah. So we're going to get our F, and then we're going to get our identity. What is it?
A.
Int A.
Yeah.
Or no, I need.
Just make it I or N or whatever.
Yeah.
You can't have your type in there. Yeah.
So let's do, and we actually have to pattern match on the tuple too as well.
Oh, because you threw a tuple in there.
Yeah, I didn't need the tuple actually. Let's just get rid of that.
Yeah.
So we do our identity IA, and then we do we do identity after I plus 1, and then...
Oh, you can't use your $sign there. You'll have to put that in parentheses. Yeah. Okay, cool. So we've got something that's purposefully breaking this So, like, this is a law that's established in, like, mathematics theory, but, like, really, it's there to make things dependable for other Haskell developers. Like, if you put this in a library,
someone would.
I'm going to expect that your functor is lawful,
Right.
and that you're not doing some weird mutations or, like, misbehaving.
Right.
Because it's perfect. Like, Haskell does not care whether or not your implementations are lawful by default, right?
Okay, cool. So yeah,
that would actually be some cool template Haskell to do, is like wrap all your types with this thing, and it'll automatically make sure that any instance that you give them is lawful, like at compile time.
Yeah, I stay away from template Haskell. I'm not good enough yet, but point taken.
Or like you could have like class lawful functor, where there's something at compile time that actually checks that it's lawful.
I bet you could do that with, if you had a fmap at the type level, maybe you could have some guarantees around it.
Yeah, I don't know.
I'm not sure.
I don't know.
Okay, but then
I mean, there's a reason that it's not in base, and
Right.
we're going to assume that that's practical.
Right.
Like, there's a reason that Haskell isn't doing it, and it might just be, you know, maybe they actually want you to be enabled to
do that,
to hack away at something.
Or it's probably.
But I feel like
it's difficult to enforce.
I feel like unlawful instances are the whole reason we think applicative is useful, but that's a whole other discussion.
Yeah. True. Okay, so then the second law is composition, which is fmap. If you fmap two composed functions, that should be, or sorry, if you compose fmaps, then that should be the same as
Fmapping their composition. Yeah.
Yeah. Oh, fmap.g.
So this is where like repeated calls to fmap are an abstraction over composition, right?
Right. This is what you were talking about. That's where I wanted to get to.
Yeah.
And this has a lot of what we talk about in Haskell is like very abstract, and usually the only justification I can come up with for being that abstract and generic is reuse. There are a couple arguments about when you're more parametric, when you're more generally parametric, you're more particular about your implementation, but I will stay away from that.
Parametricity also gives us certain guarantees of behavior that you don't get when you're not in a parametric language.
Right. I think that's what I meant with the more general you are about your or the more parametric your function is, the more specific the implementation has to be.
Yeah.
But
okay.
I think we're getting off track. This has a practical application in that if you think about fmap in terms of a list, which I think is the canonical example, as iteration, there's actually a huge performance bonus for composing your functions and only running them once, and then actually like running two iterations over the list. Now I think Haskell does some sort of like list fusion, but best not to depend on that.
Well, it's like I wouldn't say I'm at a capability where I can pick apart core generated by GHC and have some understanding of like what optimizations have been applied to the core, and if any optimizations happen after the compilation to core,
right?
Before it goes down to
Best
machine
to
code,
just
like
optimize your code yourself.
To some extent, I mean, becoming an expert in that stuff would be a great thing to do. I'm not that person yet,
right?
But like certainly, this is an optimization in any other language.
Yeah,
is like rather than running certainly with a collection, running two iterations over a collection that happens to be a functor,
right?
As opposed to running one iteration with a composition.
Right. So then I guess the challenge I put to you with your point about fmap being an abstraction over composition is I don't see that. I don't see this as being an abstraction. I see it as being an equivalence or something.
They are equivalent, right? So you can say in a language that does not have a first-class compose operator. Right.
That's what I meant by if it's. Do you mean that in JavaScript?
Yeah. Right. If we're talking about JavaScript or TypeScript, we don't have a first-class compose operator. But what we can do is stick our value inside of some functor.
Yeah.
and then
just map over it.
Also, like here, like in your example where you've got fmap f composed with fmap g, that would be analogous to like dot chaining in JavaScript.
Yes, exactly.
Or like map f over my structure on line 1, semicolon.
Right. So for
map
those...
g over the resulting structure on line 2, semicolon. Right?
Right.
It's... I mean, if you want to think about it one way, you're actually implicitly living in I/O. Like in the I/O monad, so every colon is like a bind call, kind of. But in that case, you end up with equivalent computations happening from just repeated calls to fmap.
So if I can venture to summarize, for those who aren't familiar with JavaScript, this is kind of the syntax you would have for mapping repeatedly. There is no first class composition operator. In fact, composition actually gets quite syntactically hairy with all the parentheses and the order of operations. So just being able to dot chain a map, you're basically getting a new functor that has a map function, and you're continually executing that. So it's an exercise in ergonomics as opposed to optimization, which usually JavaScript developers are fine
with. It's really just making up for the fact that we don't have first class composition. I think it would be a very different thing in other languages where you don't. Like, I guess we'll end up with the pipeline operator sooner or later in JavaScript, which is the reverse of a first class composition, but it's not there. So in Haskell, we don't need that. We don't need that garbage because we already got first class composition.
Right.
Yeah.
So I think the first point that we wanted to discuss was the name.
Yeah, like why functor and not mappable, right? Why are we...
So in the interest of making this more of a discussion, what's your opinion of the naming conventions?
So it's not going to be much of a debate because I think we're both on the same side of this.
Sure.
Although I've heard you advocate for like we should just tell beginners it's mappable.
Right. So maybe I'll defend it, but you can argue for the side that I think I've come around.
I think we get two benefits, right?
Right.
The first big and I haven't read Matt Parsons' article.
Yeah.
I really should.
That was the one that really convinced me.
Yeah.
Also, I saw a very funny tweet that said like we don't call a swan a duckable, and like is just a very concise way of encapsulating like the main point of Matt Parsons' article, which is basically that like it misses the point a bit. Like that's the conventional argument is that mappable isn't precise, but the argument that Matt Parsons' article was really promoting was that it's actually a benefit to come into something with zero context,
right? Something
that's so abstract and so complicated, rather than like the OOP pattern of giving names that have loose associations. You end up kind of like shooting yourself in the foot because you misstep. Whereas having a clean, it's like, yes, functor is hard to learn. Mm-hmm. That's why there's no associations. It's an abstract concept that doesn't have doesn't have relations to any pre-existing framework, or for most of us, no pre-existing framework.
I also I think there's a great deal of confusion between the data structure map and the function name map.
Right.
But I can definitely go along with this idea of like we're removing your presuppositions about what you're getting into by giving you this abstracted name that is kind of meaningless and that you can vaguely associate with the word function. It's clearly the same root, but like what is it really?
That was that was actually the biggest thing for me. So and that's one of the reasons Matt Parsons' article made so much sense to me, is because coming into learning functor, I was like, oh, this is just a function of some sort.
Yeah, it's a thing that uses a function.
Yeah,
it is a functor.
I think actually in OOP there is a functor, which is just like a function on an object. No, that's a method, but some sort of variation of that. I don't know much about OOP. but they actually have a separate functor.
And like in type class jargon, we like a data type is a functor, but generally we talk about it having a functor instance on a given parameter, right? Or with a given implementation. So I think there's a distinction there where like it has functor on A, right? List A has functor on A. List tuple BA has functor on A, and then you're only operating on like a slice of it.
Yeah. That's definitely something that I think that's a looseness in terminology that's uncharacteristic of the Haskell and category theory community. I mean, the terminology isn't loose in category theory. I think it's looser in the Haskell communities, and I remember when learning it, it's like so a list is called a functor, but it has a functor instance.
Right.
And what is a functor? Well, it's really just something that implements fmap. So there's kind of these three definitions that are all the same, but at the same time different. And it's not too much of a hindrance because you generally end up in the right place. But that's one occasion where category theory kind of helped me clear things up in thinking of it as a transfer. Well, I shouldn't say transformation, maybe a mapping between categories. That helped clear things up because it was the actual mapping action that was important.
Right.
Whereas the type class mechanism is really just an implementation detail of Haskell. A fantastic one. I think it's a as far as I'm aware, a novelty to Haskell. Maybe it was implemented in some other language.
I mean,
before.
it's in all of the languages that kind of live past Haskell's tradition. Like I believe they exist in Idris, and I believe I know they exist in PeerScript.
Yeah,
but
what I mean is the
like
first
the
kind of
Haskell
ML type. Yeah.
I don't know about SML. I think you mentioned you're learning.
I'm starting to learn SML, but I haven't come across type classes yet. But I was reading one of the a history of Haskell or something like that, a paper I think by Phil Wadler and Associates, and it's basically the committee that put together Haskell, and they're reflecting on what were good decisions, what were bad decisions, where did we deviate from our mission statement, and he cites type classes interestingly as a deviation, but one of the most important discoveries. Maybe not a discovery, but one of the most important features of to come out of Haskell. So I thought that was pretty interesting. But you can see how you get bogged down in this. Well, a type class really doesn't have anything to do with a functor, but a functor is something that has the type class functor, but then also a functor is something that implements map, and so it can get kind of confusing what precisely, and you can kind of feel your way through that blindness. But that was definitely like a hitch a hitch of fuzziness that I'm not used to in such a precise language.
Right. So circling back to functor terminology.
Sure.
Right. So we have this idea of we could just call it mappable, but if we give you, I think the argument that I really like is if we just call it mappable, you lose all of the reference to decades of mathematical research, and proofs that are related to functor, and essentially the laws of functor, right?
That's
it's the reference that there's some laws to this thing.
Yeah.
It's just anything with a map implementation. Well, I can think of a ton of lawless map implementations. We just showed one.
Right.
So I think that is really a good reason to actually use functor and monad and these scary older terms that aren't part of programming lingo outside of ML languages, really. Right.
Yeah, so I guess I'll offer one argument in favor of using the less intimidating words. So we run a Haskell meetup, and one of the anecdotes I heard from a HR recruiter who came to one of our meetups but works for a cryptocurrency company that uses Scala. And she was telling all of her Scala friends to come to our meetup, and they went, oh Haskell? I'm not sure if they did functional Scala. I don't really know much about them. But they were intimidated to come and ended up not showing up. And trying to drive adoption of Haskell in Toronto is difficult already, and so the fact that Scala developers, and Scala is probably one of the closest languages to Haskell in the enterprise software sense, or the easiest kind of like pseudo-functional language to drive adoption. It was surprising to me that these people were intimidated by Haskell, and so purely in a practical interest of getting people to show up, I feel like there is something less intimidating about saying mappable for Functor, saying I don't know, like concatenatable for for monoid or whatever.
And like map and concat are like some of the purest, like the first FP concepts you'll stumble across, right? Like certainly map. Like map as a method is a thing that was the first thing that you probably did as a programmer that was pure FP. Concat, I would say, like, you don't know you're flattening a monad, but or you don't know you're using monoids, but concat.
They probably are. But map is usually the first introduction to FP because it's a higher order function, and it's kind of like the canonical, aside from maybe filter. But those are the classic examples. But then of course the argument against that I found myself in is probably one of the richest understandings. One of the richest understandings I gained of typed versus untyped languages was when someone, I forget who, explained that a typed language is a category and an untyped language is a monoid. And that made complete sense. And he talked about composition in a category has to basically connect objects. So the input of one has to be the output of another. And you see what I mean? So the types enforce that.
That's really interesting.
Whereas a monoid is something where composition is anything composes in a monoid.
So like each line of an imperative language, you have like state, and we're taking in a new modification line, and we're concatenating with the kind of a monoidal sense.
I don't think that's the point he was making.
Oh, okay.
I think the point
you're talking about Komet, right?
I don't know if it was Komet.
Oh, I thought this was something you'd heard Komet say. Okay.
My mind is going to John Bays, but it might not be. But the point was that a monoid is really a category where everything composes, right?
Okay.
And that makes sense. If you've got just a bunch of strings, you can concatenate them in any ways. Those all compose in a sense. And it's the same with JavaScript. Everything composes. You might get a runtime error, but everything composes. And especially from the programming languages course that I'm learning now, they explained that in an untyped language, you basically have one type.
Yes.
Which is just like number.
So like bash is a really good example. Everything is a string in bash. Yeah.
Well, but you can. It's a sum. The main type is a sum type, so you can have as many types.
I don't even think bash has that.
No, bash doesn't have that. But the point I'm making is that JavaScript basically has one type, and every function is a function from type to type.
Yeah.
And it's basically what you have to do as the programmer is the pattern matching yourself. So when you do type of to check which type it is, you're pattern matching.
And it's implicitly throwing unsafe coerce everywhere.
Exactly. Yeah. Well, so that's the thing is type coercion. So I was giving a talk today at work, and I was trying to come up with a function that didn't compose properly. And it was actually difficult because so many things are coerced to so many other things. Like you can compose.
You'll just end up with this string object.
Yeah, you'll end up like numbers work with strings, and so I ended up just having to treat like just access fields that didn't exist. But anyways.
So we touched on this earlier, but I think this is maybe a good time to segue to higher kindedness and like how functors one must be higher kinded, but also just kind of the idea of higher kinded types.
Right. So I guess just to frame the discussion, if we go back to our class, we see that the functor f has a kind star to star. So that basically means that it's got an arity of 1. It's a unary type constructor. I'm probably using the terminology wrong, but that's the way I think of it.
Like it takes one argument, and then it's a fully formed type.
Yeah,
right?
Exactly.
So I always read the stars as type, because in pure script it's actually the word type.
I think
it's type to type.
Yeah, I think you can even do this. You might need a language extension or something.
Certainly that's the way it looks in pure script. I can't speak for Haskell.
I think if you enable gadgets not gadgets, higher kind of data, I think that allows you to actually change things in the kind system.
Yeah.
And type and star is effectively, the way that we're conceiving of star is effectively type.
Yeah.
Anyways, that's a bit of an aside. But
so it's going to take some type.
Right. But this gets a bit tricky when you have something that's a lawful functor like tuple that takes an A and a B and gives you back a tuple A comma B. So now this, if I just give it tuple, has it, maybe we'll just pretend like we're in GHC and do kind of tuple is going to have star to star to star. So that doesn't work, but we can already see from the kind we get some sort of intuition about it being curried. Mm-hmm. And I'm not sure how it actually works in the type system.
But like everything that is star to star to star, before it can become star, must become star to star, right? But I mean, anything with 3 parameters that involves currying.
Yeah, if you're going to end up with a concrete, or not a concrete, like an actual type, you have to somehow apply this down.
Yeah, I think concrete type is the right terminology.
The right terminology? Okay.
Yeah.
So how do you get a functor instance for this? Well, just as we were saying, you apply it down. So the functor instance for tuple is functor instance. The functor instance for tuple is
so you've actually got your data constructor tuple wrapped around an actual tuple, right?
Yeah, I know.
So you could just do this as like a partially
this.
applied comma operator, right?
Yeah. Sorry, what?
So, like the comma is an inline constructor for the tuple type, right?
Oh.
So,
Functor
tuple could just be bracket a comma.
I was just trying to use the type I described to make it explicit, so you could see the A B, because I want to later come back to this.
Yeah. But I'm saying for the functor instance, you can say it's a functor.
But not if I'm using my
curried tuple.
Yeah, you could, but not if I'm using my my data type.
Yeah.
Here.
So for your data type,
it'd be tuple A. I just wanted to explicitly show that it already has to have the A, and
absolutely.
The description, was it from the Haskell book? I'm forgetting where I'm learning all this stuff now, but it's that I got is that if you think of a functor as executing a function over a value contained within a structure, you can think of the additional type argument as part of that structure.
Right.
So the functor is actually over the structure tuple A, not over the structure tuple. Right.
So because it's the B that we're going to operate on.
It's the B that we're going to operate on.
Tuple by itself is not a functor per se.
Right.
Not a capital F functor. It there are potential implementations of functor.
Yeah.
But you have to give it the first parameter.
Exactly.
Because we really only care about that last parameter.
Yes. And that first parameter gets crystallized as part of that structure. That was the intuition that I got. It doesn't actually happen.
I mean, functor by itself doesn't do this, but when you get into like applicative, you have functions that require 2 values that are both of the same type. Like functor AB, like we could have like applicative where we care about the B's, so the A's have to be of the same type. So you'll actually have to have like it'll be specified to tuple int something, right?
Does applicative care about that? I thought applicative.
Yeah. So if you have an applicative for like tuple with an int and a bool in the first position, like one with an int and one with a bool in the first position, and then they happen to have the second parameter, they are not of the same type. Those types won't unify.
Right.
Do you see what I'm saying? Think about it with an either, right?
Right.
So with an either, if you have an either string and an either error, something that comes up an awful lot, right? So the left would be left for the first structure would be a string.
Yeah.
Left for the second structure would be an error.
Right.
Some enum error type that's out in the world.
Yeah.
It doesn't matter that your rights happen to be the same type.
Right.
Because the functor instance isn't over the same type.
Right.
That
okay,
first
I see what you're
parameter,
saying.
if it's a parameterized thing, the item filling it must be of the same type.
I see what you're saying.
Right?
And
So,
same with the plicative.
so
Right.
lift A2, for example.
Right.
Right.
But you're effectively saying the same thing, is that this first type needs to be crystallized or needs to be held constant for the applicative.
Right. And
Right.
so if you have any function that's going to take two things of the same type at a functor level, and it's got some type variables that precede the thing that you're going to be operating on, precede B in this case for tuple,
Yeah.
then the A must be the same type.
Yeah.
Yeah.
You're
Yeah.
right. So that's we're
Yeah.
saying the same thing different ways. So yeah, good point. So that's the first part of higher kindness, but the second part that fell out of it for me was that when you have a true functor, I guess is what I'll call it, but basically a data type like identity, where if I take the kind of identity that I described above, it's star to star, and so that's the kind that the functor expects. So basically every value in that data type, every value in the term will get transformed by the A to B function in functor.
Okay.
But if you have a kind that needs to be applied down, you're going to have some values that get ignored. And that's, I think, most obvious in the conjunctive type, the algebraic data types, basically, product and sum.
Right.
Because product and sum usually require they require two types. Sorry, they don't require two types, but they take two types, and sometimes they can be different, and when they're different, you need a kind of star to star to star.
Right. So you could have a tuple A that's just a pair of A and A.
Right.
Right, but you could also have a tuple AB where you've got B and A in some combination in your tuple, right?
Right. So you could have this tuple, which is A to A, and then you could have data tuple prime, which is AB equals AB. So the first one has the kind that works with the functor, star to star, but the second one is star to star to star.
I think for people watching now or in the future, I think it should be noted this is not necessarily going to compile. This is kind of pseudo Haskell.
Yeah.
Yeah. But this is the idea. Like you have some data tuple A that will, like I think you'd need a constructor there for it to be data, but like it could be type tuple A or something.
Well, I'll just add a constructor because the point of this is that I want to show the type variables and how they work. You can do it with a new type or something. But anyways, the point being that the A's in tuple prime are going to get skipped by the function, by the fmap function. And so that behavior arises differently. Well, it's basically the same across products and sums, but when you have a sum, it's indeterminate which you're going to have. So sometimes it will skip the transformation and sometimes it will execute the transformation, right? If you have an A, it's going to skip it. If you have a B, it's going to execute the transformation, right? But then for for product types, it will always execute the transformation, but it will just ignore the first part. So for this example, the A in the tuple would never get mapped over, would never get transformed, but the B would. So No, I guess the different ways that behavior arises in FMAP is kind of interesting. Like we were talking about how it abstracts over null checks for like a maybe.
Yeah, for a sum type.
Yeah.
We're abstracting over we talked a lot about the word iteration, and I think you had some feelings about iteration, but like a maybe is isomorphic to a list of length 0 or 1.
Yeah.
Right? So it's iteration 0 times or 1 times, depending on whether or not you have a just or a nothing, right? And either, as far as FMAP is concerned, is exactly the same. If you have a left, I don't care. If you have a right, then I'm going to do something, right? So it's 0 or 1. If you have a list or something isomorphic, like any collection that happens to be a functor, then we're going to iterate more times, right?
Right.
And I think we talked about for sum types, because with a sum type, every instance of A in a sum type that we care about for FMAP is required. There's nothing optional about it, right?
Sorry, can you...
So for a tuple of AA,
yeah,
you need 2 A's. You can't just magically not have an A.
Type. You mean a product type.
Sorry, for a product type. Yeah, for a sum type, you're talking about 0 or more times.
Yes.
For a product type, we're talking about
we need to have
at least once, possibly. Like if A occurs more than once in the data structure, then we must do things multiple times.
Right.
So I think that's where you got into iteration, where I think my conclusion on it was more that's abstracting parallel execution of our function provided to map. Because in one step we must fmap both A's.
Right.
Right? So we get into like kind of abstractions over control arrow.
Yeah.
But
yeah,
like,
I think we got into that with exponentiation.
Right, because product types. Well, we'll get into exponentiation because that's a whole discussion from our afternoon chat.
Yeah.
But like for a product types are generally isomorphic to tuples, right?
Maybe I should switch it back to share the screen because
we're not really doing a whole lot of coding. But product types are generally isomorphic to tuples, right? So if we have a tuple of 3 parameters, right?
Mm-hmm.
If 2 of or certainly a pair, like everything that you could need to do to implement FMAP for any pair that you can construct,
you will always have the values.
Well, those functions already exist in control arrow, right? It's all like you have ID on one side and like $sign on the other, right?
Control arrow is getting a bit advanced for me. I mean, I don't.
Control arrow is a thing that when you get into it, it like pollutes all of your code with those techniques.
Right.
But like, I mean, essentially, it's a set of like generalized lenses over tuples. That's what's in control arrow.
Sure. What could you explain it to me without using control arrow?
Yeah, sure. Like, all that we're doing is for any value that is not our A in that product type or tuple.
Yeah.
We're just running ID on it. For any value that is our A, we're applying our function.
Right.
Right.
But in a true functor, you're not running ID. You're just leaving. I mean, I know that they're like isomorphic, but maybe it's a way to think about it. But
okay, so remember our unlawful functor that took an int?
Yeah.
If we were to make a lawful instance for that, it would have to still take that int and give it back.
Right.
You're running ID.
Right, I guess.
Yeah.
So, yeah, that's true. So it is like the arrow. But where are we going with this?
Well, specifically, I'd be talking about the star arrow, which is parallel execution of 2 functions on a tuple.
I figured you were talking about the fan.
Fan out goes the other way. Fan out is 1 value to 2 values in a tuple.
See, I don't know control arrow.
Control arrow is so fun though.
But I to bring it back to the larger point we were talking about, FMAP will happen 0 or 1 times on a sum type.
Mm-hmm.
It will always happen on a product type.
Perhaps multiple times in parallel. Like if you've got 2 A's.
Yeah. But you will always run the function, and depending on the kind, it might not get run. And then, the other
types.
Well, before we even get there, I was fascinated by how FMAP the implementation of fmap over recursive types abstracts iteration.
Yep.
So that was interesting to me. And at first I thought it was products, but I really realized it was recursive. So basically like lists, trees, I think you said anything isomorphic to a list. But that was really interesting to me. It's funny because the way that realization happened for me was it started with just a fascination of the behavior. And I think at first I was like, oh, fmap is this generic concept that if you understand, it actually abstracts over all these different things. But then I realized it actually doesn't abstract over that many things. It just abstracts over null checking and iteration, as far as I've seen.
Well, within Haskell's type system.
Within Haskell's type system.
Right.
Sure.
So
we're talking about Haskell here.
We're isolated to the category of Hask.
Yeah.
But like, at a category theory perspective, this makes sense because a functor takes a particular value and pulls it to another category.
Right.
Which may live within the same category if it's an endofunctor.
Right.
But then map's whole thing is to take the hum set of functions that operate on that value and lift them into arrows that live within the mapped category, right?
Right.
And
another way of saying that is that a functor in category theory will not just map objects, but it will also map relations in terms of arrows.
Yeah.
Functions.
Yep.
So you're mapping functions, and that's why
you're mapping the hum set of functions that operate, or the hum set of arrows that operate on the objects within the original.
I don't know if it's a hom set, because I thought a hom set was a set of arrows from an object to another object.
Yeah.
Yeah, but it's the set of all functions in that category.
No, that only operate within on the particular object that is inside of the functor.
But every object in the category
a functor is not required to operate on every object with like that. Then you get into applicative where you can put any arbitrary value inside of your functor. A functor is not required to have that.
I'm pretty sure a functor has to map every object in a category to an object in another category. It can collapse.
Okay, but it doesn't have to. I don't believe it needs to. The category that we're referring to does not need to be the entire category of Hask. It could be a category of numbers to a category of some other value, right?
Right. So I guess you're looking at it from more. I'm trying to think of it in a more general category theoretic sense, where the category that is the input to the category that your functor is mapping from. Basically, the functor has to include all of the objects and functions from the category that you're mapping from. They can be condensed in the category that you're mapping to.
Right. But I mean the
kicker for example is a limit.
Yeah. The kicker for that though, like the thing that ends up being useful is now we can abstract over any given structure.
Right. Exactly. That's exactly right.
Yeah. So we talked about product and sum. Should we dive a little bit into how it abstracts over exponential types?
Yeah.
So
why don't you start?
Yeah. Let me.
Do you want some code?
I'll switch over to my Vim.
Sure.
And we'll go from there. So I think that's 6. Hey. This can close. We don't need this. Just Vim. Hey, that is not the right workspace at all. There we go. So we're in Vim. Let's say we have reader, right? So I'm not even going to use the new type wrapper. We just have some function that's an A to B, or A to R, right? So we're going to take
Isn't it R to A?
Yeah, we can do it that way. I've seen it expressed so many different ways, but we have some function.
Yeah.
We're not going to care about this R too much. We're really talking about being a functor on A. And when we map onto things, onto this function that's going to be our reader function, we don't really care about what the argument is. We only know that whatever the argument is, it's going to result in some A. Yeah. So concrete, like we have a function from some environment to int. We're going to generate an int. And then we can do things, we can map over that int if we're to make that a concrete type. So in this case, map is perfectly equivalent to the compose operator. right?
Right.
Because we don't know about what argument it's going to get. We only know it's going to result in some int, and we can provide things.
Why don't you write out the whole type? Like, write out the whole data type and write out the actual type of map, because that was, and then make it
sure.
Make it null point free, because that was super useful for me. Is like just seeing the implementation that it's composed. It's like, great. Okay, now I get that it's composed. But what's really interesting is how you get from the types to the implementation. Specifically, how like the only reasonable path from the types to the implementation is compose.
Okay, so we have data reader R,
Yeah.
A is equal to this reader wrapping over R and A.
They're
Like
not-
we could actually do like,
they're not seeing code.
let me just take a look. Oh, let's just take a look there. Can you see code now? Just rotate around here. I see code.
Yeah, but I think you're missing the data.
Oh yeah,
You're cut
totally.
off.
That's where they weren't seeing code. Okay, well let's just bring that into screen.
You want to switch it to me, and I'll just type it out.
I've got it.
You got it?
Yeah. Let me just. Oh, there we go. So hopefully in just a moment we'll see the data constructor.
No, I think it's cut off on the left.
Oh.
Yeah.
Hang on. I see what's going on. Let's do that. There we go.
There you go.
Yeah. So hopefully that resolves not seeing code.
Yeah.
So we've got like a data reader RA to reader, and we're going to give it like a little run reader method here. Oh. There we go. Backward. Reader. So we have run reader. Should probably capitalize that guy. And it's going to be of type R to A.
Yeah.
And
Close that product. Yeah.
Close that off. Okay, so now we got reader. And so then we would say like it's going to have an instance functor reader R where. So now we can
parens around the parens around the reader R.
Oh yeah. Cool. So reader R is going to take some A at the type level, and now we're going to have some map method. All right. So map is going to take some F.
Yeah.
And it's going to take a reader of G, we'll call it, or I like to call it like Ra. So it's a function from R to A.
Yeah.
And I'll write up kind of the full type for this as well.
Yeah, that's great.
Yeah.
Because I found for me that like I always have instance signatures on in my type classes, but like the instance signatures language extension, because it like I like seeing my signatures before I write them, especially if it's a complex one. Like if it's fmap, I generally know it, but yeah.
Yeah, fair enough. So okay, its type is going to take some function from R to B. We're going to have reader R A to, I'm missing an arrow over here. Reader R B. Yet another arrow. Okay, reader R B. Okay, so now we can see that we're going to kind of pull out the RA, and we're going to apply the F somehow to it to end up with a B. Now in this case, that B, that's going to be the result of the function, and so we need something to go from R to A to B, because F is of type A to B, and end up with an R to B. That's pretty much the rote type of the compose operator.
Right. So actually, if you make the type, like, just get rid of the reader and treat it as like a function,
right.
I think that makes it more clear.
Oh, totally, yeah. So we're taking some RA,
Yeah.
And here, we'll just strip out the reader new type, or the reader data type constructor there. And we'll just make that R to A. And R to B.
Right.
Yeah.
So the idea being that the eventual type is actually R to A to B, but because you've composed it, you've it's not actually R to A to B, because that would be like currying, but you get my point, that it's like, yes, you're just basically putting you're basically attaching the ends of the function, and that's just composition. Yeah, exactly.
Yeah. So if we call our f AB, because it's a function from A to B, and we've got our reader, RA, we can just pull it out and say AB composed with RA, which we can make point free by just saying it's just the compose operator. So what we found in our discussion this afternoon, I don't know if there's an exception to this, but any functor that contains a function, so reader, state, any kind of state derivative that you can think of.
I guess any functor over a function type.
Yeah, any functor over a function type is going to need to use compose in order to implement its functor instance, because you can't make a concrete type from a function using fmap.
Right.
You're providing a function to another function. The only thing you can really do is arrange the functions somehow fancy, right?
Yeah. So I guess the argument I was making, although I think we generally agree that to some degree, any functor over a function abstracts over composition.
Right.
I think there's no way of getting around it that something's going to be composed. The point that I was trying to get at was that it doesn't always involve the composition of the A to B function that you're getting. And I guess the reason I said that is because literally any function you have in, well, maybe not literally any function, but most functions I can think of can be rejigged into a point-free state just by composition.
Right.
There's like a website, it's called like PointFreeMe or something.
PointFree.io.
Yeah, PointFree.io, that will just turn any polymorphic function into a set of basically a bunch of variables and compositions. Mm-hmm. And so I think the challenge I gave to you was to make state, the state functor, demonstrate that, or implement the state functor only with composition, and your solution was the control dot arrow. So it was composition of a kind. But the point that I was trying to make is that, like, yes, you can rearrange these things and compose them in different ways, but really at the end of the day, the F is just getting applied to something, and the composition is happening outside of that.
Right.
So, take from that what you will. I think generally your sentiment is correct.
Yeah. So what's interesting is the state function. I've pulled out the state constructor, so we just have a function from S to tuple of beta S. The resolution I showed you to that was something like this. Let me just... I'm going to get rid of the type real quick just to talk about this. So what I found is, jumping in here, we had map is going to have an F and SAS, and we're going to execute SAS to get some AS, and then we were going to compose that with the control arrow. So F is going to be applied to A, so we're just popping that in there, and then ID on the other side. So we're just going to keep the same S that we get out, and now we're returning a new tuple with some different A in it. And what is interesting about that is we have a function returning a product type, and that control arrow operator abstracts over the product type part, and compose is abstracting over the function part.
Right. That's I think the point you were making, but if I can figure this out, I think.
Should I switch back over to your screen?
Yeah, maybe switch back over to my screen.
Sure.
And I think if we use a lambda instead of your.
You're not sharing your screen on the chat.
Right.
Yeah.
Let me share my screen. So if we switch back over here, we've got f. So f is our a to b, and we actually want to take our s and apply that to say some lambda, which is going to pattern match on. Oh, hold on. We want to. Sorry, I'm mixing up my s's. Let's call this our state. And we're going to take s and apply that to our state. So now we've got an as. And then we've got some sort of lambda that's going to take an a and an s and give you back. Oh my god. It's going to give you back an fa comma s. The point that I was trying to make is that you can really just do this, where you take some s, you apply it to state, you get back that I'm going to actually have to make this s2, call this s1, just so we can keep them straight.
So hang on, let me understand this implementation. So we're going to take some s, and where are we getting the second tuple from? This argument in the second lambda.
Which, this?
Yeah.
We're pattern matching. So state is my first argument here.
I think you want a let statement there rather than a second lambda, bud.
You could, but you don't need it. The point I was trying to make is I was trying to use a lambda instead of the instead of compose.
Yeah.
So we could make this lambda take a function and pass it in, right? Like we could. That's basically what your star, what is it called? Anyways, your control.arrow function was doing. Right.
Sure. Okay.
That's effectively what it's doing. Then we have to pass in f.
Oh, I see.
You see
so you've built the whole map up out of
right.
Like this is super not point free. Okay.
So what I'm saying is that yes, there is composition, but if you break down the implementation details of that, I don't know what you call the operator, that control.arrow piece, it ends up just being a function that's gonna apply the f to the a. So when I write it out like this, the composition is completely obfuscated.
Oh, absolutely. You can't tell that what you're really doing is shuffling deck chairs around on the composition.
Right. And so
Titanic.
the greater argument that I would make is, okay, you can reshuffle this and write it in terms of composition, but you can do that with almost any function in Haskell. So is it really composition at its core? And I think we agree that generally yes, but maybe not as far as Haskell's concerned. That's the point that
you don't need to use the composition operator in order to implement composition.
Right,
I think whatever solution you will find
would you say that
will
this
be
is
equivalent.
Faithfully composition?
I can't speak to whether or not this implementation will
actually
compile,
what you could do. Wait. So actually, this is what you did, right? That's what you did. Yes.
Is it?
Yeah. So
you've lost me a little bit on this implementation because it's just not how I would go about implementing
right.
it.
So maybe it'll be more clear if I use if I say where. What are we calling this? This is going to be AP. Sure.
I mean, I think this is actually the canonical implementation of functor over state.
So that there is composition.
There's composition.
There is composition there. So this is probably closer to what you wrote.
Yes.
But the argument that I was making is that the f is never composed. The f is just applied to the a, and so the argument you were making is that actually if you run the operator you're using, the composition is being run in parallel.
Right, okay.
Over the tuple, so you're saying that
I think you want to be applying S1 to your state there at the end.
Yeah, you're right.
Yeah.
That's exactly right.
Okay, now I'm kind of tracking what's going on.
Right. So I've just implemented the function that you used without passing f in explicitly.
Yeah, you're still using compose there, but you use
the compose operator, but the f isn't being composed is the point that I was
No, you're not necessarily directly composing f.
Right.
Because we're actually dealing with a product type as the result.
Right.
You have to use some kind of arrow-ish thing.
Right.
Some generalized arrow where you're applying f in a specific position in your product type.
Right.
And then eventually you're going to end up with something that you can compose with the function inside of your functor.
Right.
Right.
But I guess the takeaway is that if we go back to what we were saying, some type is either applying or not applying the function.
Mm-hmm.
Product type is applying the function to the A, and if there are other types that exist that aren't A, don't apply them.
And like running within a structure, right? So we have 6 things, but we only need to care about 1 or 2 of them. Right.
And in fact, we only can care about one of them.
Right.
With a faithful functor.
Well, we could have 2 A's, right?
Yeah.
So we could have 6
but I mean,
things.
if we have 6 types.
Yeah, 6 independent types, well then we're only going to care about 1 of them. But if we have like 6 parameters, 2 of which are the same type.
Yeah.
Yeah.
And then function or exponentiation types end up being composed of some sort. At a general level, you are composing functions in a way that gets you the result.
Cool.
So I think we can take that, even if there are some qualms about the implementation. So maybe as a final point, we can talk about polarity.
Sure, like the polarity of a functor. So you can have like contravariant, covariant, and invariant functors.
Right, that's exactly correct. The point that was more interesting to me when I was learning is I got confused. I was conflating the functor with the functor instance with covariance and contravariance. So I was thinking, okay, I've got this functor instance. This is a contravariant functor instance, which you can't have. There's actually a type class for contravariance.
Yeah, because they don't follow the same laws.
They don't follow the same rules or the same patterns. But the important part is that it's not actually the functor instance that is covariant or contravariant. It's the position of the types.
Right.
So maybe I'll start writing and you can start introducing covariance. I think we'll start with that.
So covariance would be most functors that you can name that aren't contravariant. So in this case, we're talking about like, it looks like you're writing a product type so far.
I was going to do a function.
Function works.
To show.
Oh, okay.
Just
so a covariant on a function.
Yeah.
Covariant on a function means that it's to the right of the arrow, or to the right of an equals sign, if you want to talk about it that way. So it's a thing that you have. So when you talk about functors as containers of things, this is the thing that's going to be on. It's going to exist at some point, right?
Yeah.
So and you have some A, you map it to some B, and now you have a functor that's full of B's, right? Don't let them get out; they may sting you. So a covariant function really cares about the thing that's going to exist. So it's easier to reason about covariant functors as containers of stuff, or things that will eventually contain some stuff. In the case of a function, we don't have it yet. Later we're going to execute the function, then we're going to get NA, and that's why we're using compose to kind of construct out a path for that.
So this is what we had already implemented. But basically, any function type that is covariant is the variable or the type variable as defined by the kind is the return value.
Right.
So,
and like you can reason about it in terms of the arrows that the map function takes, right?
Right.
So the map function is going to take something from A to B and go from B to C. And anytime you're kind of looking at something that abstracts over like syllogism or modus ponens from a logical perspective, then you're looking at a covariant functor.
Right.
Where map it has the arrows that kind of follow modus ponens.
Right. I see what you're saying. It's above my pay grade. But.
So, like, I have an A. I have a thing that says A's can become B's, so then I have a B, and then I have a thing that goes B's to C's, so then I can chain them all together and say I can go from A to C.
Right.
That's when you're talking about covariance. It's very good for linear thinkers.
Right. So what I like to do is if we take the function functor instance, and I like to actually section the function type so that you can see that it's returning a B, and we have actually a function from.
But you wouldn't put your instance functor that way. You'd actually put it the other way if you care about the B's for a covariant.
Sorry, you're right.
Yeah.
I got confused. Yeah.
So B to A.
Yeah. It's
a
B to something.
We've curried the function operator there.
Yeah.
And so it's going to take some
A. So now if we specialize this, we see that we've actually got a B to an A, or sorry, let's call it X to just completely establish that it's different.
Right.
So now what we've got is the type of our functor is actually X to A.
So then it would be X to B. Yeah.
Yes, and so then we need an X to B. And so now it becomes very obvious what needs to happen is composition. We have to pre-compose. But if we have something that's contravariant...
You can just like copy-paste, can't you?
I can, but actually I'm going to just do the instance. Oh, maybe I'll do both.
Do them both.
Sure, I'll do both. So this, if we paste...
Yeah, so now we can make contra.
And I'll actually flip these. It actually doesn't matter as long as you just like flip the way that they're applied. But
yeah.
So now we can see that our functorial type. I really should come up with a name for it.
We care about the input, like the target, the item we have a functor on.
I want to call
in this case is the B.
I want to call it the free type, basically the unapplied type or something like that. But I know I'll probably get in trouble. But basically the B is what we care about. So then if we
That's all Haskell's about is we lord over each other with our intellect.
With our naming conventions.
And naming conventions. And we don't get any real work done. We just argue a lot.
So now if we see that we've got this contravariant type, I'm basically getting rid of the constructors just so it's more obvious. We can see that we've actually, well, maybe I'll write it out faithfully first. We've got some f of A, and we want to go to some f of B, right? Oh no, it's the opposite actually.
Yeah, so
this is what messed with me so much when I was learning it, because I didn't learn. Oh, this isn't functor actually. This is contravariant.
Yeah, it's contravariant functor.
See, I still got messed up by it, but the and this is contra map. So sorry,
your argument would be contra. Yeah, contra map. Yeah.
So this contra map, and we'll just get rid of the implementation for now. But this type signature kind of like haunted me.
Yeah.
Because it's a function from A to B, and then a functor over B. How on earth am I going to get an A?
Right.
It doesn't make sense. But once you understand the function instance of functor, it becomes much more clear. Because you've seen that, hey, this composes, well, now things are reversed and the type signature is reversed, this probably composes as well. So maybe if you explain it, I'll specialize it.
Contramap kind of does the rain dance backwards a little bit. So where in a covariant functor you go from A to B and B to C, contravariant, because we're dealing with stuff on the other side of function equality, we're going from B to A, right? We go from C to B, B to A to Z, and we're going backwards a little bit.
Right.
So we have some function that's going to take an int and produce a string. well, then we can put something that'll take a bool and produce an int on the front of that, and now that still works. So it's the flipped compose operator.
Right. And so if I can get this straight, I think that it's actually G after F.
Yeah.
I believe it's flipped. Or you can, I think some people do it this way. They do flip.
For anyone who's like really beginning but has stuck with us through an hour and a half of obtuse functor discussion, pronouncing the compose operator as after lended so much to my readability of Haskell.
That's a good point. That's how I consider it as well. But yeah.
Yeah, reading. I think it was Bartosz Milewski who was the first person to say, like, you can pronounce this as after, and it works.
And it makes sense.
So G after F. Yeah, that's absolutely consonant.
So that makes sense.
So we're going to perform F. We're going to get some A out of F.
Yeah.
And then we're going to provide that A to G, right?
Right. And so then the canonical example of this is predicate, and you can probably see it from the type, but if we make a predicate type, which will take some A and gives us back a predicate, get pred, we'll call it, of type A to bool, obviously. It's kind of obvious that...
you want to capitalize your bool. Otherwise, it's a parameter. Yeah. But anyways, go ahead.
Yeah, and that's obviously contravariant because of the position. So I think we skipped over polarity, but basically,
well, I think this kind of illustrates polarity.
It illustrates polarity, but the meat of the matter is that anything in the first position of the arrow has what they consider a negative sign. I think Sandy McGuire's book says this, and George Wilson has a talk on it as well. That A is the parameter position is negative, and the return position is positive, and product and sum types are all positive, and you get a covariant. You have a covariant type when the type that the functor cares about, the free type, as I was calling it, is covariant, and you have a contravariant functor where you would need the contravariant instance when the type that you care about is in the parameter position. Right. But you can have some complexity added. You can have I'll just call it like data complex, where you have an A and complex, get complex, and you can have something like this where you have A to B. I need to parameterize it, but call it int to call it bool, whatever. This is actually covariant,
right?
And the reason for that is because the polarity mathematics follows the same intuition you would have for multiplication. So a negative position multiplied with a negative position gives you a positive position. Right? Or a positive polarity, I should say. So this A is in the negative position, but then the whole expression is also in the negative position, so then that combines.
It's been a while since I looked into this, but doesn't it correspond exactly with exponential math and like the way the types in a function deal with exponentiation, the covariance of a given...
Probably does, knowing this stuff. Like everything ends up being math.
Yeah.
But probably the I think that probably makes sense that it corresponds to the mathematics of exponentiation. Although I thought, that does make sense actually. Now that I think about it.
Yeah. I mean, I could be totally out to lunch. Like, I really hope there's no one out there taking everything we say as rote, but we kind of have an idea of what we're doing. I think we're both perfectly able to write some decent code in Haskell, and related languages. It's just this is also a shooting the shit.
Yeah. So I guess
I think this might be a good place to kind of conclude today.
To wrap up.
Yeah.
I guess I would like to couch it with the caveat, if anybody is actually listening,
or in the future,
if you're listening to this, that don't always know what we're talking about. If anyone wants to correct us, we're welcome to that. If not, that's fine too. We'll just carry on making mistakes. But we are just that, liable to make mistakes, and so this is just as much for us as it is for anyone else. And it's more about having a discussion about these things and hopefully opening that discussion up to a wider audience so that we can learn from people as well.
Yeah.
So I guess that's just the to reiterate the mission statement.
Yeah, I think we're going to be putting this up on YouTube, so hopefully in the future YouTube people can comment on this and tell us how wrong we really are.
Yeah, and future us can look back and tell us how wrong we really are.
1 week in the future,
Yeah.
We're going to just have egg on our faces.
Yeah.
But I think for now, this has been the inaugural episode of what we're thinking might be purely functional pleasantries.
Yeah, the maiden voyage.
Thank you to anyone in the chat for joining us, and always feel free to ask questions. My name is Ben Hart. You can find me on Twitter at dev_productive. What's your Twitter, John?
I think it's Jonathan Lorimer 1. So basically my name without the R at the end and a 1.
All right. Well, thank you all for watching and listening to us ramble, and hopefully we'll get another episode out
Soon.
Updated some days.
Yes.
All right. Thanks, everyone.
Bye.